So we've seen a little bit about how we can use Spark to explore some data in a data frame, and we can use Spark SQL to query that data frame as a table, and we can get some information about the statistics and the relationship between the values in that data. And all of that is going to help us as we come to build a machine learning model. So let's take a look at that. Well, here I am back in my notebook, and we've done all of our analysis of the data. We're ready to train a machine learning model now. And you might remember we cleaned up the data, we removed the duplicates, we fixed the missing values, we balanced the data so there's an equal number or a roughly equal number of flights that were late and flights that were delayed. And we got rid of some of the outliers for our delays so that the more extreme, unusual cases aren't in there anymore. So what I'm going to do now is I'm going to take that data that I've got, that I've cleaned up, and I'm going to split it into two data sets. I'm going to split it 70% versus 30%. And the reason I'm doing that is this is an example of what we call supervised machine learning. We're going to build a classification model that classifies whether a flight is likely to be late or not. So there's two classes, and that's a form of supervised learning. And what we mean by that is we already have some historical data that tells us about flights that were late or not. And I want to use some of that to train a model, but I want to keep some of it back so that I can then validate the model with records where I already know whether it was late or not. I can check that the model is predicting accurately. So we've gone ahead and we've split that data up, and we now have a slightly larger training set than a test set. It's just 70% of our data is going to be used for training, and we've kept 30% for testing. So now what we're going to do is we're going to define something called a pipeline. Now, pipeline is a useful way of taking all of the steps that we need to apply to the data and making them happen in a sequence, and then bundling that together as a single object called a pipeline that we use to perform all those actions and then train the model. So in this case, there's a number of things that I want to do with the data. The month and the day, although those are numbers, they're integer numbers, I actually want to treat them as categories. They're not numbers that we count. You know, we don't take day number 5 and add it to day number 4 and get day number 9. So it's not that kind of number. So we treat them as categories. There are 7 days in a week. Each one we can think of as being a different category. And there are 31 days in a month. And again, we can think of those as categories. So we're going to take those and we're just going to treat them as if they're strings and get an index for each one of them, for each distinct value. So we're not treating them as numbers. We're treating them as categories. The same is obviously true of the carrier, which is, of course, a string. And the same is true of the origin and destination airport IDs. So we've got a number of these different indexers that we're using to take those columns and convert them into indexes that just represent the category for those things. Then the next thing we're going to do is we're going to take those indexed columns that we've created and also the departure delay. These are going to be what we call the features that we use to train our model. Features are aspects of the data or characteristics of the data that have some impact or conceivably some effect on the thing that we're trying to predict. So we'll take those features and we're going to use those. We're not using the arrival delay because obviously if we were going to use this model to predict whether a flight is going to be late or not, then we wouldn't have the arrival delay because the flight hasn't arrived yet. So we haven't got that field in here. We've just got the data that we can use to predict whether or not the flight will be late or not. So those are my features. And then I'm going to use those features to train a logistic regression model. Logistic regression is one of a number of algorithms we can use for classification. And in this case, that's what we're going to use. So logistic regression, the label column that we're going to train is late. So late has a value 1 or 0. Those are my two different classes. So we're going to try and predict whether a flight is late based on those features. And then there are a couple of parameters that I use to control the way that the logistic regression model is trained. So we'll apply some regularization to avoid what we call overfitting the model to the training data, and we'll iterate through that model a maximum of 10 times as we train it. So all of those things that I've done there, those different steps to do the indexing, assemble the different vectors for features, and the logistic regression model itself, those are going to be the stages in my pipeline. So we'll do our indexing, then we'll assemble the features, and then we'll train the logistic regression model. And we do that by defining that pipeline and then using the fit method to apply that to our training data. So we'll fit the training data to the model. Well, let's go and run that cell and take a look at what happens. It'll take a little while to run. And when it finishes running, I've got this pipeline model. It's just given it a unique identifier. I've got this pipeline model now that I can use to predict the lateness or not of new flights. I can use that to predict that label. So, well, you might remember we held back some data to test this model with. So we've got some data where we already know if the flight was late or not. So we can apply that test data to our model, and we're going to get back some columns. We'll get back the features it was trained with. The raw prediction is a vector value that's used internally to determine what value, what class it's going to predict. What actually gets produced by a classifier is a probability for each of the different classes. So we get the probability, and that will always add up to 1 across all of the classes. And then based on that probability, with a default threshold of somewhere in the middle, it's going to come up with what the actual prediction is for that class. So we're going to get that. It comes back as a decimal, so we'll just cast that to an integer. And then I'm also going to bring back from my test data the true label. In other words, what was the flight actually late or not? So we get our predicted class and then the actual true class for the data that we already know about. So we'll go ahead and run that. And what comes back from that is this set of values here. The features is a vector, the raw prediction is a vector, the probability is a vector with a probability for each of the different classes. The prediction that it comes up with is an integer, and then the true label that it actually was is an integer. And here's the first 20 or so rows. And I can see immediately I've got some here where the prediction was 0, but the true label was 1, so that one's wrong. Here the prediction was 1, the true label was 1. Here the prediction was 0, the true label was 0. So I can see as I scan down those first few rows, there seems to be some decent performance going on here. We seem to be actually predicting relatively accurately. There's one or two that aren't right, but it seems to be about right. And I can see the probability here. The probability of the first value here is probability of it being 0, probability of it being 1. And you can see that actually that's pretty close. A 0.53 probability that it was 0, a 0.46 probability that it was 1. And that kind of goes some way to explaining why it got that one wrong. It was nearly right, but it was just the wrong side of the threshold. So how do I actually measure this a bit more scientifically rather than just scanning through and seeing which ones it got right? Well, I can gather some metrics based on the results of that testing with my test data. And the thing I'm really interested in are these 4 core values. Are true positives, in other words, we predicted 1 and it was 1. Our true negatives, we predicted 0 and it was 0. Our false positives, we predicted 1 and it was 0. And our false negatives, we predicted 0 and it was 1. So those are 4 kind of core metrics, and we use those to form what's called a confusion matrix. So we'll go and run that and get those values back. And from that confusion matrix, we can actually calculate some other more meaningful metrics. So we'll just let this run and take a look at these metrics. And out comes my results, and I can see the true positives and true negatives have the significantly larger values, and that's a good sign. That shows me that the ones that are true, I'm getting more of them true than not. The false negatives is slightly higher than the false positives, so that we're kind of erring on the side of false negatives. And then from these, we've calculated some other metrics. Now, the most obvious thing to look at is accuracy. In other words, what percentage of my predictions were correct. And in this case, it's got an accuracy of 0.88, or just under 89%. Now, that might sound really good, but the problem with accuracy is if we have imbalanced data, like we saw earlier on, where we have many, many more flights that are on time than are late, then, of course, I could just simply always predict 0. I could predict that every flight is on time, and if 90% of my data is flights that are on time, then my model is 90% accurate. It just isn't very good at predicting flights that are going to be late. So accuracy is one of these numbers that it's kind of useful as a kind of top-level metric, but it doesn't really give me the whole story. I'm more interested in things like precision and recall. Now, precision is the number of true positives out of the number of true positives plus false positives. In other words, out of all the things that I predicted were positive, out of all the flights I predicted were late, how many were actually late? So we get our precision figure there. And I've got just under 94% of those. So out of all of the things that I predicted were late, around 94% of them actually were late. And then I've also got this this recall value, which is a slightly different way of looking at things. And this is saying that out of all the things that actually were late, out of all the flights that were late, the true positives and the false negatives, how many did I predict? And in this case, I predicted just under 85% of flights that were late I actually predicted accurately. So those metrics give me a little bit of confidence in my model that it's certainly better than 50%. It's better than just guessing whether a flight is late or not. And I can validate that by looking at something called the area under the ROC curve, the received operator characteristic curve. Now, the ROC curve itself is a way of viewing for every possible threshold value where I might decide if a probability means a 1 or a 0, what's the true positive rate and the false positive rate. And that calculates a curve. The important thing about that curve is I want to compare that curve to a line that's diagonally across it that basically says this is what I would get if I just guessed 50% of the time late, 50% not. And what I get back for my area under my actual curve for my predictions is just under 95%. So it's certainly performing much better than I would if I just guessed a 50-50 guess as whether the flight was going to be late or not. And that metric, that area under the curve metric, is a fairly standard metric that we use when we're evaluating a binary classifier like this, which is why there's a function for me to do that within Spark. And I'm getting a pretty decent result from that model that I've built. It's reasonably good at predicting whether flights are going to be late or on time.